Hello, today we are following up our introduction to ionic compounds. We're going to use some Lewis dots to transfer of valence electrons in the formation of ionic bonds. So one of the things you may have seen before is that transfer of electrons when using a Bohr model. The Bohr model is great, but it shows you protons, it shows you neutrons, it shows you the total number of valence electrons, and the total number of electrons. Oftentimes we only care about the valence electrons because those are the ones involved in our transfer. So the nice thing about Lewis dots, the Lewis dots allow us to see specifically just the valence electrons and their transfer that occurs when we are forming an ionic bond. So first thing we need to do is be able to identify our valence electrons. As a review, if you look at the periodic table and you look at the column, on this particular periodic table, all the columns with an A are directly tied to your valence electrons. So if I'm in column 1A, I've got 1 valence. If I'm in column 6A, I've got 6 valence. If I'm in column 7A, I've got 7 valence, so on and so forth. So we want to look at sodium and fluorine. Sodium is going to have 1 valence electron, and fluorine is going to have 7 valence electrons. And that's going to be my starting point here, 1 and 7. Then again, same thing we talked about before with ion formation. We have to ask ourselves, what's the easiest route? I can either lose 1 or gain enough to get to 8. And gaining 7 takes way too much, so I'm going to lose 1. And then I can also lose all 7 or gain 1. And gaining 1's the easier option here. So now that I know that I'm going to lose 1 and gain 1, I have to think about my charges. Remember that electrons are negative, so if you're losing something negative, you're going to become positive. So sodium ends up with a +1, fluorine ends up with a -1. So it's gaining 1 electron. For the Lewis dots, you just need to write the symbol. So I've got sodium symbol and 1 dot to represent my valence electron. For fluorine, do the same thing. I can draw in my 7 dots. You'll notice that one of those spaces is open. So I'm going to go ahead and I'm going to show that transfer of my valence electron by using an arrow, and I'll just point to that open space. Now that sodium has lost an electron, there are no more dots per se. We know that the energy level below technically has 8, so you could draw in 8 dots for sodium, but it lost the 1 valence that was part of the reaction, and so we're just going to write sodium with its charge. Fluorine, on the other hand, now has all 8 dots, and so we can use brackets and write 1 minus on the outside. Now the question I always get in first year chemistry, does it matter whether the plus sign is on or before the number or after the number? Does it matter if the minus sign is before the number or after the number when we're talking about charge? Officially, yes, there is a correct way to do that. One way refers to an oxidation state or an oxidation number. The other way refers to the charge. In a first year class, I'm not going to really worry about it too much. For those going on to an AP course, we'll address those concerns when we get there. Next thing I have to look at is my formula. The formula is just the formula of the compound. Even though I drew in lots of dots here, I'm just looking at the number of atoms I drew when I write my formula. For sodium, I drew 1 atom, so I write Na. For fluorine, I drew in 1 atom, so I write F. We know that technically each of these should have a subscript of 1, but we don't ever write the subscript when we only have 1 of something. So the formula for sodium fluoride is just NaF. Now, let's go back and reevaluate some things. We know that ionic bonds are electrostatic attractions, meaning that they are between elements that have opposite charges when they are ions. One of the things that we need to point out is that those charges have to balance out so that way we have an overall neutral compound. If I add +1 and -1 together, sure enough, that will equal 0. So I know I have a neutral compound. Let's look at another one and see what happens here. We've got calcium and chlorine. Calcium is in the second column, it has 2 valence. Chlorine is in the 7 column, it has 7 valence. So we've got 2 and 7. So we can ask ourselves, what's going to happen with calcium's valence electrons? It's going to be easier to lose 2, and I'll end up with a +2 charge. I can either lose my 7 or gain 1. It's easier to gain 1, so I still end up with a 1- charge. Now, if I added these two charges together, +2 and -1, I get a net of +1, which is not a neutral compound. So I have to figure out exactly how to represent this with Lewis dots, because things are going to get a little tricky. We can draw our Lewis dots as normal. I'll draw my chlorine compound, or my chlorine atom, sorry. And just like before, I know that one of my valence electrons can get donated to chlorine. And this chlorine on the left here is now going to have its 8, which is great. And it'll form its 1- charge. Calcium, on the other hand, still has a valence electron it needs to get rid of. We said it's going to lose both of them because it wants to have a full valence shell. If it's not just going to lose one because it's still unstable. So what can we do? Well, you have to remember that when these reactions are occurring, we've got trillions and trillions and trillions of particles usually reacting together, especially when you think about what a mole is. A mole is 6.02 times 10 to the 23rd atoms. If you've got a mole of a substance reacting with another mole of a substance, you've got a lot of stuff. There's essentially just a very, very large amount of atoms available. So we can just bring in another one. And that last valence electron can get donated to chlorine. Calcium has lost both of its valence electrons. It now has its 2+ charge. My second chlorine is going to end up with a 1- charge. And now, if I add up those charges, -1 plus a +2 plus a -1 will equal out to 0. So now we've achieved a neutral compound. Then I just have to ask myself, okay, the formula. How many times did I draw calcium? I just had one calcium atom here. Don't need a subscript for it. How many chlorines are there? Sure enough, there's 2. So Cl and then a subscript of 2 to represent the formula there. Now, drawing this is great because you can see the transfer of electrons, but in the next lesson, we're going to look at how to actually write these formulas without having to draw the Lewis structures every time. The periodic table, is actually a huge key to figuring these out without having to draw. If we know what our valence electrons are, we also know what our charges are for each column. So that's something we'll keep in mind as we go into the next lesson. Using those patterns are going to help us figure out how to write the formulas for ionic compounds. And there definitely are going to be some ionic compounds forming with these ones, the transition metals. Those ones are unique. We'll talk about the different kinds of charges that those can have as well. All right, see you next time.